Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on January 15, 2026, just 2 days ago. It presents a new autonomous agent called ML Master 2.0, which uses a hierarchical memory system to achieve a state-of-the-art medal rate of about 56% on OpenAI's MLE bench. The paper is titled Toward Ultra-Long Horizon Agentic Science, Cognitive Accumulation for Machine Learning Engineering. And as we'll see later, this new approach to cognitive caching offers a promising blueprint for scaling AI autonomy in complex research environments. For those interested in the implementation, the authors have shared their code on GitHub. Figure 1 details these results, breaking down performance by task difficulty. The legend in the top right identifies ML Master 2.0 by the striped blue bars, contrasting it with the original version in light blue and other agents in gray. Focusing on the all group on the far right, we see the new model reaches a 56.4% medal rate, nearly doubling the score of its predecessor. Crucially, this lead holds up even in the high complexity tasks shown in the third cluster, proving the system's robustness. So, having seen the performance gains, Figure 2 diagrams the framework that makes them possible, called hierarchical cognitive caching. On the left, the agent executes code in the environment, generating a busy stream of results. The system organizes this information into 3 tiers on the right. The bottom layer, L1, captures evolving experience, storing raw traces like code and terminal logs. Above that, L2 holds refined knowledge, which distills those logs into judgments. Finally, the top layer, L3, preserves prior wisdom, allowing the agent to prefetch high-level strategies like model templates. While the previous figure outlined the memory structure, Figure 3 demonstrates the dynamic flow of information through what the authors call context migration. On the far left, the context prefetch mechanism starts a new task, here identifying apple leaf diseases by summarizing the problem and querying the L3 cache to retrieve relevant prior strategies, like using specific image augmentations. In the center, the context hit phase assembles these retrieved strategies with real-time logs and refined knowledge to drive immediate code execution. Finally, the right column illustrates context promotion, where the system takes the messy results of those experiments, distills them into concise insights, and saves them back to memory for future use. So, having explored the mechanism, Table 1 compares performance on the MLE bench. The top section lists proprietary baselines, including OpenHands and the strong competitor Liru. The bottom section highlights the open source category with ML Master 2.0. Looking at the average medal rate column, the new model achieves 56.4%, beating Liru's 50.7%. This lead holds in the low complexity column as well, where ML Master 2.0 hits nearly 76%, confirming the strategy scales effectively. Alright, proving that these gains come from the architecture itself. Table 2 breaks down an ablation study. Here, the authors selectively disable the memory tiers to measure their specific contributions. Notice in the first row that removing the L1 experience layer is catastrophic. The medal rate crashes to roughly 23%. This happens because the agent cannot track its immediate interactions. By comparison, the highlighted bottom row shows that combining experience, knowledge, and wisdom boosts the medal rate to nearly 73%, confirming that the full hierarchical structure is essential for success. So, having seen the components, Figure 4 illustrates their efficiency during a live task. On the left, the agent progresses through 4 sequential research plans for the Random Acts of Pizza Challenge. The graph on the right tracks the accumulating memory cost with the token count on the horizontal axis. Without management, the orange line shows the context growing uncontrollably, reaching over 200,000 tokens. However, the blue line reveals the cognitive caching advantage. It fluctuates and drops repeatedly because the agent actively compresses its history, capping usage near 70,000 tokens and allowing it to solve the task efficiently. Wrapping up, 2 takeaways stand out. First, simply expanding context windows is not the solution for long-term autonomy. Instead, ML Master 2.0 proves that structuring memory hierarchically, separating immediate experience from long-term wisdom, is essential for sustaining complex research without getting overwhelmed. Second, this cognitive accumulation model offers a scalable blueprint for the future of agentic science. That's it for this episode of the AI Research Roundup. I'm Alex, thanks for listening.